Hi, and welcome to the sixth lecture of machine learning course. In this video, I'm going to talk about the advanced practices, and I'm calling it advanced practices not necessarily because the techniques here are more complex or very sophisticated, but specifically because they are applied in some very specific contexts. Uh, in many situations, you will most likely not need to start using these techniques, but sometimes they're quite helpful. So let's begin. I'm starting with handling imbalanced data sets. Often in practice, you see the examples of classes when we're doing classification, for example, in the training data that they are underrepresented. And what I mean by that is that the data set is not uniformly distributed between different classes. It could be that you have one class with 10 examples, the other class with 2 examples, and one class with 100 examples. And in this case, it would be a bit difficult for your learning algorithm to learn probably what it needs to know. For example, when the classifier has to distinguish between genuine and fraudulent e-commerce transactions, then of course the examples of genuine transactions are much more frequent. And in this case, for example, if you use support vector machine, like what you're seeing here in this picture, with soft margin, you can define a cost for misclassified examples. And because noise is always present in the training data, then there are high chances that many examples of correct genuine transaction would end up on the wrong side of the decision boundary by contributing to the cost. Support vector machine typically try to move the hyperplane to avoid as much as possible misclassified examples, and the fraudulent examples, the yellow ones for example here, that are a minority, risk being misclassified in order to classify more numerous examples of the majority class correctly. And this is what you're seeing in picture A here. The problem is observed for most learning algorithms that are applied to imbalanced data sets. And if you set the custom misclassification of examples of the minority class higher, then the model will try harder to avoid misclassifying those examples. Uh, as you see, some support vector machine implementations allow you to provide weights for every class, and by that you could avoid this misclassification to some extent. So that is one of the ways of handling this imbalanced data set. But what if a learning algorithm doesn't allow weighting classes? In these situations, you can try, for example, the technique called oversampling, and it consists of increasing the importance of examples of some classes by just making multiple copies of that of the examples of that classes. Getting back to the example that I said at the beginning, let's say you have 100 examples in one class and 20 examples in the other class. You simply can copy the dataset several times so that you get the balanced dataset with equal distribution in both classes. I mean, you could go the opposite around as well. You could do undersampling and then to randomly remove from the training dataset some examples of the majority class. And you could do that if you really have enough data on the class with the small number of examples. So basically what I'm saying is that if that number is already good enough, then you can start cutting from the class with more number of examples. You might also try to create some synthetic examples by randomly sampling feature values of several examples of the minority class and then combine them to obtain a new example of that class. And there are two popular algorithms that oversample the minority class by creating synthetic examples. The first one is the synthetic minority oversampling technique, SMOTE, and the adaptive synthetic sampling method. And both of these methods work similarly in many ways. Both of them randomly pick all possible xi's in dataset and then try to create new examples. Uh, so, and you should keep in mind that some algorithms are less sensitive to the problem of an imbalanced data set. For example, decision trees, random forest, and gradient boosting often perform actually quite well on imbalanced data sets. So you don't need to take care of these sort of data sets in all machine learning problems that you're facing, but you need to keep in mind that if that was making a problem, there are some techniques to overcome that issue. Another advanced practice is called combining models. You remember ensemble algorithms like random forests that would typically combine models of the same nature. And by that, they boost performance by combining hundreds of weak models. In practice, we can sometimes get an additional performance gain by combining strong models made with different learning algorithms. And in this case, we usually use only 2 or 3 models. There are three typical ways to combine models, and they are, as you see here, averaging, majority word, and stacking. And averaging works for regression as well as those classification models that return classification scores, not necessarily classification classes. You simply apply all your models, let's call them base models, to the input X and then average the prediction to see if the average model works better than each individual algorithm you tested on the validation set using the metric of your choice. Majority vote works for classification models. You apply your both model to the input X and then return the majority class among all predictions. And in case of a tie, you either randomly pick one of the classes or you return an error message saying that uh, you are not sure what the class is. And finally, stacking consists of building a meta model that takes the output of base models as input. And by that, I mean, let's say you want to combine classifier F1 and F2 and both predicting the same set of classes. To create a training example for the model uh, example xi and yi hat for the stacked model, we should set the new input as the output f1 of x and f1 2 of x of the both previous classifiers and then output with the same. If some of your base model return not just a class but also a score for each class, you can use these values as features too. And to train the stacked model, it is recommended to use examples from the training set and tune the hyperparameters of the stacked model using cross validations. Obviously, you have to make sure that your stacked model performs better on the validation set than each of those base models you stacked. Otherwise, there is no usefulness in the new model that you have built. And the reason that combining multiple models can bring better performance is the observation that when several uncorrelated strong models agree, they are more likely to agree on the correct outcome. The keyword here is uncorrelated. Ideally, base models should be obtained using different features using algorithms of the different natures. For example, support vector models and random forest. Combining different versions of decision tree algorithms or several SVMs with different hyperparameters may not result in a significant performance boost. Okay, now let's get to the neural networks again. And since you have practiced so much during this course with neural networks, you have already some questions, and probably this part is going to answer to them. In neural network training, one challenging aspect is to convert your data input to the input that network can work with. For example, if your input is images, first of all, you have to resize all images so they have the same dimensions. After that, pixels are usually first standardized and then normalized to a range between 0 and 1. Another example is text. Texts have to be tokenized, which is splitting them into pieces such as word, punctuation marks, and other symbols. For CNN and RNNs, each token is converted into a vector using one-hot encoding, so the text becomes a list of one-hot vectors. Another, often a better way to represent token is by using word embedding, and you have already done it in your previous mini projects. For multi-layer perceptron to convert text to vectors, the bag of words approach may work very well, especially for larger text. Uh, then, so data is one thing. The other thing is the choice of the neural network architecture, which is generally a difficult one. For the same problem, like a sec-to-sec learning, sequence learning, there's a variety of architecture, and new ones are proposed almost every year. So there is really nothing that you can stick with it forever. They are always changing, and you need to give them try to find a better model. And this is actually one of the things that I wanted you to pay attention to specifically. Now, in both your mini projects, you had the chance to use neural networks. The first one you were supposed to use it, but in the second one you could have chosen one architecture of the neural network, or even two. It could be recurrent, it could be convolutional, or anything else as the architecture of your choice. And what I have observed in most of your project was that you are sticking to the simplest possible architecture. You in many projects, I don't say all, you really didn't try to add layers, you didn't try to make the architecture more complicated. And then some of you faced with the problem of accuracy, you couldn't really increase the accuracy of the model because your model was too simple for the data set that you were working with. So this is important. If your model didn't work, sometimes it is good to change the architecture. And because of that, I recommend searching the state of the art solutions for your problem in the internet. And that was actually the purpose of the second mini project. If you read carefully in the project description, I said that one very important feature of a good machine learning expert is to be able to find these solutions that he or she hasn't heard of yet. So what I wanted you to do was to search, to look online how you can find the best efficient model. How could you increase sorry, the efficiency of your model? So keep that in mind. Necessarily the first solution you find is not the best solution. So in practice, the advantage of modern architecture over an older one becomes less significant as you pre-process, clean, and normalize your data and create a larger training data set. Modern neural network architectures are a result of the collaboration of scientists from several labs and companies, and such models could be complex to implement on your own. So this doesn't really defy what I just said before, that you need to look for a more complex solution. Uh, what I'm saying here, the modern ones are actually very more complex than what I'm talking for normal in-class projects. And that is one of the reasons I really don't set the accuracy to 95, 97% for you. I typically say if you have a model with at least 80% of accuracy, you have a good model in hand. Uh, so data architecture, but then after that, after you decide on the architecture, you have to decide on several different things: number of layers, their type, their size. And it is recommended to start with one or two layers, train the model and see if it is fitting the training data well, basically if it has a low bias. And if not, gradually increase the size of each layer and the number of layers until the model perfectly fits the training data. Once this is the case, if the model doesn't perform well on the validation data, meaning that it has a high variance, you should add regularization to your model. if after adding regularization the model doesn't fit the training data anymore, it slightly increase the size of the network, sorry. So you see, it is just iteration and iteration and iteration until you get to where you want to get. Don't give up easily on your model if it didn't perform well at the beginning. There are several different things that you can try. You can increase the number of layers, you can change their size, you can change the type of the layers that you're adding, and more stuff I'm going to just say in a minute that you can do to the neural networks. Change the learning rate, change the uh, hyperparameters, add dropout layer, earlier stopping, batch normalization. And now that I already mentioned them, let's get to the advanced regularization. We have already talked about L1 and L2 regularization before, but you can use neural network specific regularizers as well. And they are dropout, early stopping, and batch normalization. Uh, the last one technically is not a regularization technique, but if it often has a regularization effect on the model. So the concept of dropout is very simple, and I shall already say that it is very powerful and impactful. Each time you run a training example through the network, you temporarily, by adding a dropout layer, exclude at random some units of the computation. The higher the percentage of the units excluded, the higher the regularization effect. Neural network libraries allow you to add a dropout layer between two successive layers, or you can specify the dropout parameter for the layer. The dropout parameter is in the range of 0 and 1, and it has to be found experimentally by tuning it on the validation data. Early stopping is another approach, and it is the way to train your neural network by saving the preliminary model after every epoch and assessing the performance of the preliminary model on the validation set. Uh, so what it does is basically we have the possibility of adding several checkpoints in our neural network model in Keras. And what earlier stopping does, if that it checks if the next model or two next model, it basically depends how long you put your patience value. If the performance is dropping out, basically it stops the training and save the last best model based on the patience value that you have chosen. And patience value is basically meaning how many more epochs it waits to stop the training. Batch normalization, it could also be called batch standardization, is a technique that consists of standardizing the output of each layer before the units of the subsequent layer receive them as input. In practice, batch normalization results in faster and more stable training, as well as some regularization effects. So it is always a good idea to try to use batch normalization. And in neural network libraries, you can often insert a batch normalization layer between two layers. Uh, Another regularization technique that can be applied not just to neural networks, but to virtually any learning algorithm is called data augmentation. This technique is often used to regularize models that work with images, and you're going to see it in, what was the example now? In transfer learning hands-on practice that I'm going to show you today. The technique is often used to regularize models that work with images, as I said, and once you have your original label training set, you can create a synthetic example from an original example by applying various transformations to the original images. It could be zooming it slightly, rotating it, flipping it, darkening it, and so on. And you can keep the original label in these synthetic examples. In practice, this often results in increased performance of the model. Okay, so another thing that I want to discuss is handling multiple inputs and outputs, which comes after this. often in practice you work with multimodal data, and by that I mean your example could be image and text and the binary input all together. That this binary output could actually indicate whether the text describes this image or not. It is hard to adapt shallow learning algorithms to work with multimodal data. It's of course not impossible. You could train one shallow model on the image and another one on the text, and then you can use the model combination technique as we discussed before. If you cannot divide your problems into two independent sum problems, then you can try to vectorize each input and then simply concatenate two feature vectors together to form one wider feature vector. With neural networks, you have more flexibility. You can build two subnetworks, for one for each type of input. For example, a CNN subnetwork would read the images, while a RNN subnetwork would read the text. And then both subnetworks have their last layer as an embedding. CNN has an embedding of the image, while RNN has an embedding of the text. And then here is when you can concatenate two embeddings and then add a classification layers, such as softmax or sigmoid, on top of that concatenated embedding. And it is really easy to do it in neural network libraries that you have seen so far, Keras, for example, to use such a thing. In some problems, on the other hand, you would like to predict multiple outputs for one input. An example of this is what you have already seen in the previous lecture, and that is multi-label classifications. Some problems with multiple outputs can be effectively converted into a multi-label classification problem, and however, in some cases, outputs are multimodal and their combination cannot be effectively enumerated. Uh, think about the following example. You want to build a model that detects an object on an image and then returns in coordinates. In addition, the model has to return a tag describing the object, such as person, cat, I don't know, dog, building. Your training example will be a feature vector that represents an image, and then the label be represented as a vector of coordinates of the object, and then another vector with one hot encoding tag. And to handle a situation like this, you can create one subnetwork that would work as an encoder. It will read the input image using, for example, one or several convolutional layers, and the encoder's last layer would be the embedding of the image. Then you add two other subnetworks on top of that embedding layer, one that takes the embedding vector as the input and predicts the coordinate of the page, and this subnetwork has a ReLU as a last layer, which is a good choice for predicting positive real values such as coordinates. And the second subnetwork would take the same embedding vector as the input and predict the probabilities of this tag. And this subnetwork can have a softmax as a last layer, for example, which is appropriate for probabilistic approach output. You should remember that we are interested in accurately predicting both coordinates and the tags. So it is impossible to optimize two cost functions at the same time. And if we try to optimize one, we can risk hurting the second one or the other way around. What we can do is that we define a new hyperparameter in the range of 0 and 1, and then define a combined cost function between the cost function of first subnetwork and the cost function of second network. And then this is where we try to tune this new hyperparameter. So this is how we could manage multiple outputs. And now let's get to something that is very interesting and it could be useful for you in several different contexts. Transfer learning is probably where neural networks have a unique advantage over the shallow models. In transfer learning, what you do is to pick an existing model on some data set, trained on some data set, and then you adapt this model to predict examples from another data set, different from the one that the model was built on. And the second data set is not like holdout set that you use for validation and tests. It may represent some other phenomenon altogether, uh, or it could be even from another statistical distribution. For example, imagine that you have your model trained to recognize wild animals on a big label dataset. And after some time, you have another problem to solve. You need to build a model that would recognize domestic animals. With shallow learning algorithm, you don't have many options. You basically need to build another big label dataset for these new domestic animals and then train a model on that. With neural network, the situation is easier to handle. Transfer learning in neural network works as you see on this slide. First, you build a deep model on the original dataset, that was the wild animals. Then you compile a much smaller labeled dataset for your second model, which is the domestic animals. After that, you remove the last one or several layers from the first model. Usually, these are the layers that are responsible for classification or regression, and they usually follow the embedding layer. After that, after you remove these ones, you replace the removed layers with new layers adapted for your new problem. You freeze the parameters and you're going to see all of these in practice, so that is a bit easier to digest then. You freeze the parameters of the layers remaining from the first model, but that you don't train them anymore, you keep them as they are. And then you use your smaller labeled dataset and gradient descent to train the parameters of the new layer. Usually, there is an abundance of deep models for visual problems online. So you can find one that highest chances to be used for your problem, download that model, remove several layers, put your own prediction layer, and train the model. And if you don't have an existing model, transfer learning can still be something that you could use when your problem require a label dataset, very costly to obtain, but you can get another dataset for which labels are more readily available. Let's say you built a document classification model, and you got the taxonomy of the labels from your employer, and it contains 1,000 model a thousand categories. In this case, you will need to pay someone to read, understand, and memorize the difference between categories and read up 1,000,000, for example, documents and annotate them. But to save on the labeling so many examples, you can consider using Wikipedia pages as a dataset to build your first model. The labels for the Wikipedia pages could be obtained automatically by taking the categories the Wikipedia page belongs to. Once your first model has learned to predict Wikipedia categories, you can fine-tune this model to predict the categories of your employer's taxonomy. And then you will need much fewer annotated examples for your employer's problem than you would need if you started solving your original problem from scratch. Okay, so that was about the theory. We can now move on and see how transfer learning works in action. See you in next video.